so the first thing we're going to do is I have this water right here. You see it's on the hot plate, and it's not quite boiling, but it's really obviously very warm. And then I have this other water that I actually put ice in, so it's really cold, okay? And I'm going to drop food coloring in each one, and you're going to observe what happens, okay? The hot versus the cold, okay? So the first thing I'm going to do is drop 2 drops of food coloring into the hot. Y'all ready? 1, 2. Okay, so observe what happens. Yeah?
Wait, for a word, I know it's not like absorbed within water. What would you say?
Dispersed, spread. Okay, so now I'm going to drop it into, actually I need to set this on something because it's not high enough for people at home. Now I'm going to drop it into this cold water. There we go. And we're going to notice what happens. Okay, ready? Can y'all see where? Okay. Now, if you look at question number 2, it says, adding heat energy makes water molecules move faster. Use this fact to explain your observations. So go ahead and answer that question in number 2. Okay, now looking at the next demo number 2. I have this beaker right here of water that's heated. And I'm going to take this bottle of water and I'm going to put this cap right here on upside down, right? So it's not all screwed on, it's upside down. And I'm going to put the bottle into, oh, that one's slipping. Might have to use the other bottle because this one's greasy. I used that other one first period, so it might be a one-trick pony for this one. All right, so I'm going to put the top this way, okay, and I'm going to put the bottle into the hot water. Let's see what happens. Can you see the cap moving? Can you hear it? Why is the cap moving? Why is the cap moving? It's on upside down, so there's no reason for it to move. Why is it moving? You see it? Yeah? So that's the next question. So write down your observation, and then why do you think the cap was moving? Okay, are y'all ready for the third one? Okay, so for this one, I'm going to put bubble solution on the top. So it's right here, okay? And then I'm going to take the bottle and I'm going to put it back in the water. Look what happens to the bubbles. Okay, now, what do you think is going to happen if I put it in the cold water? Oh, didn't work. Try it one more time. What do you think is going to happen when I take the bubbles from the hot and put it into the cold? See? It comes back in, and then it comes back out. Oh, it popped. It only works if it doesn't pop. And out. And in. Yeah. All right, so write down your observations for that one. Okay, and then your question, heating a gas makes molecules move faster, cooling makes them move slower. So use that to explain what happened. And then in the very last one, match the room temperature cold water and hot water to the picture that you think best represents the molecules. Okay, so for the next thing, we're going to watch a quick video, and I mean quick, like it's 2 minutes. There's a question that I posed in Google Classroom. So if you'll go to the question and open up the question, I'll play the video up here. Those folks at home will have to watch the video on their own, and you can answer the question after you watch the video. Okay, so y'all tell me when you're ready.
The video questions?
Yeah, it says video question. But I would go ahead and open it so that you can answer it. You're ready to answer it. And I don't know about you guys, but I like to read the question before so I know what I'm looking for. So if you want to go ahead and read the question real quickly, and then I'll play the video. And the video literally is 2 minutes, so don't blink. You're going to miss it. Now give me a thumbs up when you're ready.
Wait, both questions?
Yeah, they're connected. And the video is going to tell you. Ready?
Mm-hmm.
Are you ready? Okay.
What's a sheet of ice now evidence of a battle raging far below Antarctica's surface that may drastically reshape the Earth. The Associated Press recently spent 2 weeks with scientists on the remote continent, searching for answers to 2 pressing questions. Why is the ice melting, and what does this mean for Earth's land and coastlines?
One of the biggest challenges globally from all of this warming, this melt, is that a lot of the human population lives near sea level. A lot of big cities, a lot of agricultural land, a lot of vulnerable coastline.
Nowhere is this melt more apparent than here on the Antarctic Peninsula, where temperatures are rising the fastest. Water from the warmer ocean is slowly heating away the ice, melting an additional 130 billion tons per year, enough to fill more than 1.3 million Olympic swimming pools, and the rate is speeding up. Biologist Angelica Casanova has been tracking plants and stones deposited by retreating glaciers for 2 decades. Great indicators, she says, of the changing climate.
As we know, Antarctica has been the place that has registered the biggest increases in temperature. We have had approximately an increase of 3 degrees in the last 50 years.
While only a few degrees warmer, scientists say that small change can make a huge difference over time.
97% of the Antarctic Peninsula is still covered by ice, so it's not that it's all melting, it's all going to go away just like that. But a small amount of that ice melting is enough to make a significant contribution to the water going into the ocean, which makes a significant contribution to sea level rise.
Scientists estimate it could take 200 to 1,000 years to melt completely, enough to raise sea levels by 10 feet, which could have a costly impact on coastal cities like New York and Mumbai. A change so gradual, but one that occurs with every drop. Maggie Mazzetti, Associated Press.
Okay, so take a minute to answer the questions.
Well, what does it mean? What is happening on an atomic level? Like, what does that mean?
What do you think is happening to the atoms?
Oh.
Okay, so as soon as you submit that, open up the notes sheet. And we'll go through the notes. Y'all give me a thumbs up when you're ready.
Wait, did you say we need to take notes on this?
Yeah, it's in the sheet's there. Yeah, for you just to fill in. It's one of the assignments, so it's in classwork. You see it? Matter notes.
Is it energy and blue?
This one's for you, so it doesn't matter. Yeah, thank you for asking though. Yeah, blue is for the things that you turn into me that I have to be able to find the answer. Because it's really difficult, at least for my aging eyes. All right, so physical science, right, is half chemistry, half physics. So if you took chemistry, you would have chemistry the whole year. If you took physics, you'd have physics the whole year. Physical science, you have chemistry for part of the year, and we have physics for part of the year. So I like to say it's chemistry light and physics light. So you get the best of both worlds because you get the introduction to both concepts without having to choose one or the other. So right now, we're in the chemistry section. So chemistry, by definition, is the study of the composition, structure, and properties of matter, the processes that matter undergoes, and the energy changes that accompany these processes, okay? That's a whole big definition that basically says this. We're going to study matter and how matter changes, right? That's what we're going to study in chemistry, okay? All right, so the definition of matter we've talked about before, but it's anything that has mass and takes up space, right? So matter is anything that has mass and volume, okay? Anything that has mass and volume is matter. And remember we talked about in the very beginning that things are either matter or energy, right? If it has mass, it's what? Matter. If it has no mass, then energy. This one is extremely important that you follow the exact wording because there's two parts to this definition. The kinetic theory of matter is all matter is made up of one, tiny particles, right? And two, that are in constant motion. You got to have both pieces. So the kinetic theory of matter states all matter is made up of tiny particles that have energy and are in constant motion, okay? And that's the premise of everything that we're going to talk about. Matter consists of particles with energy, particles in motion. Now, in elementary school, maybe even in middle school, you called matter states of matter, right? Solid, liquid, gas. We're not going to call it states. We're going to call it phases of matter. And we're going to discuss the phases of matter, what happens to the particles during the phases of matter, and then how do we change phases, okay? So what are the phases that we have? Solid, liquid, gas, right? And then what's the fourth one that we always forget? Plasma, yeah. So the common phases are solid, liquid, and gas, right? But we also have this plasma phase, okay? So let's watch this quick video. Somewhat dated, but still good. On plasma.
Hi, my name is Michael Sweat. I'm a junior at the University of Maryland, College Park. This is Bobby Bruce. He's a grad student here as well. And we're here to tell you about plasma, the core state of matter. And we're here researching plasma to find out how plasma can be made to create some pretty amazing phenomena. So I hope you enjoy this video. Thank you. Plasma. It is the basis of some of the most spectacular phenomena of nature. The violent spark of lightning, the luminescent northern lights, even the burning brightness in the core of every star in the universe, all have their origin in plasma. Man-made plasmas include fluorescent light bulbs, neon signs, and plasma televisions. When we think of plasma, we often think of its intense otherworldly glow, which almost seems supernatural. However, plasmas contain underlying physical concepts. So what is a plasma? Let's first look at a gas. A gas has a positive core with the negative electrons orbiting around the core. A plasma is a gas that is heated to the point that the individual gas atoms break apart into a collection of positively and negatively charged particles. flow of a plasma is created by the occasional recombination of negative and positive charges. This recombination produces an emission of light with the color determined purely by the gas chemistry. In a laboratory environment, plasmas can be reproduced by flowing a gas into a vacuum chamber and igniting this gas with electric power. Depending on the type of gas flowing through the chamber, plasma can take on many rich colors. In the vacuum chamber, you can see argon gas emit purple light. Nitrogen emits a reddish-orange light, and fluorocarbon emits blue. All of these different colors are specific to the gas chemistries. Plasmas can be used as a controllable reactive gas. So for example, if we put an object at the edge of the plasma, the charged particles will bombard the object, etching away at the surface. The electronics industry has used this concept in smaller and smaller patterns into silicon, which is used in laptop computers, cell phones, and a whole wide variety of other applications. Plasma processing proved essential to the rapid miniaturization and increased performance of computers. These plasma processes are integral to the information revolution that is occurring today. Here at the University of Maryland, scientific research will continue to advance our understanding of plasma and its applications to make a better future.
All right, so that gives us plasma. Now, I think this video is a little bit dated. It's still got good information, but I think we have a lot more uses for plasma now. We know we have plasma screen TVs and whatnot. But this was a little bit at the beginning, really, when they were trying to figure out how to harness it. Okay. All right, solids. Solids hold their shape. They have definite volume and definite shape. Okay. Solids hold their shape. They have definite volume and definite shape. However, the particles in a solid are still moving. They just don't change positions, right? So we think of them more as vibrating in place, right? Because they're still in motion. They're just not changing positions. Okay, we have two types of solids that we have to be aware of. One is a crystalline solid. Say that, crystalline. Crystalline. Yeah, crystalline solid. It has a lattice-like structure, right? Which means it has a very uniform structure, right? That if you look at it under the microscope, you can see the very structured uniformity, right, of the molecules. Okay, they're all set up in a very easy to follow pattern. That is the crystalline solid. We also have solids that don't follow this pattern. These are the amorphous solids. Just say amorphous. Amorphous. Yeah, that's a weird word too. Okay. Amorphous solids are kind of like waxes and glass and plastic, things that don't have necessarily a uniform structure, but they still have a solid properties, holding their shape, having definite volume and definite shape. Okay. The word amorphous means having no form. You see how in this example of the molecules, the crystalline molecules are set up in a very easy to see pattern, and in the amorphous solid, it's not exactly uniform. How about liquids? Liquids have definite volume, right? But do they have definite shape? No, the liquids are going to take the shape of whatever container you put them in, right? And I know in the middle school, one of the examples they do is they take the same amount of liquid and they pour it into a wide bowl and into a skinny bowl. And they show you how it looks like it's more if it's in a glass versus a wide bowl, right? But it's really the same volume. Deceiving. Now, remember we said that the particles of the solid don't change positions. They more like vibrate in place. The liquid particles do change positions, but they stay close together, right? But they do change positions. How about a gas? What do you think happens with the particles of gas? Do they change positions? Yes. Do they stay close together? No, right? Gas does not have definite volume or definite shape because it will take the place, it will take up all the container, right? All the space that's provided. When we talk about gas, we also talk about gas pressure. What is gas pressure? Think about a balloon. If you were blowing up a balloon, when you first start to blow it up and there's not a lot of air in it, is there a lot of pressure on the balloon walls? No. But as you continue to blow and you put more and more air in that balloon, is there more pressure on the walls? Yes, absolutely. Okay. That's what gas pressure is. It's the gas molecules inside of a container putting pressure or force on the walls of the container, right? And the pressure increases when there's more molecules in the confined space, right? So do you think volume has an effect on pressure? Yeah. All right, plasma. We talked about plasma. Plasma is a gas-like state of matter, right, or phase of matter, only the particles rearrange. So it's more like they have collisions, right? They're colliding and they're putting off this extra energy, right? And that's how we get that glow. All right, super important. The definition of temperature is not how hot something is, right? The definition of temperature is how much energy is in the particles or the molecules of a sample of matter, right? The definition of temperature is the average kinetic energy of the particles in the matter. Now, if the particles have more energy, they're moving more, is it going to be hotter? Yes, right? But the definition of temperature is not how hot it is, it's how much energy is in the particles. How much energy is in the particles. So, if we have particles of solid, right, and we increase the heat applied, you will raise the temperature. Do you see that? That's how that works. If you increase the heat, you raise the temperature. By increasing the heat, I allow these particles to have enough energy to start to separate, right? That moves them from a solid to a liquid. If I continue to increase the heat, the temperature or the energy of the molecules will increase even more, and they will be able to get further and further apart, which will put them in the gas phase, right? So in order to have a phase change, I have to increase the energy of the particles, right? One of the ways I can increase the energy of the particles is by giving heat, applying heat, right? And heat, by definition, is a transfer of energy. All right, what are the phase changes that we have to know? Okay. Melting. What's melting? What phase am I going from? Solid to liquid. Good. Freezing. Okay, what's happening when I freeze? Liquid to solid. Good. Vaporization. Yeah, liquid to gas. Very good. Y'all know these. Condensation. Gas to liquid. Yes, ma'am. Condensation. Gas to liquid. You ever had somebody tell you that their glass is sweating? Yeah, is the glass really sweating? No, the glass isn't sweating, but the gas molecules around, right, are turning into liquid. How about sublimation? Sublimation. I'll give you a hint, dry ice. Go solid to gas, solid to gas. Sublimation is solid to gas, okay? And how about this one, deposition? Snowflakes. This is the opposite of sublimation. This is gas to solid. Gas to solid. So when snowflakes appear, they are going straight from gas to solid. They don't go through liquid phase. If they go through liquid phase, what we get is freezing rain or sleet, right? All right. Now, to go from a gas to plasma, it's called ionization, and go from plasma to gas, it's called deionization. okay? That's adding some extra energy to those molecules. We don't really do a whole lot with that, but just be aware that that's how it works. But this is basically what we said. Solid to liquid is melting, liquid to solid is freezing, right? Solid to gas, sublimation, gas to solid deposition, liquid to gas, vaporization, gas, liquid, condensation, yeah? So you need to be familiar with that diagram, okay? All right, now, how do we get from one phase to the other, okay? Well, to go from ice to water, your molecules have to absorb heat. They have to take in energy, right? But to go from water to ice, they have to release energy, right? Temperature is dropping, we're releasing energy, okay? That has a name. You ready? When I take in energy, that's called endothermic. E-N-D-O, endothermic. When I release energy, that's called exothermic. E-X-O, exothermic, okay? Can you think of any other term that has E-N and E-X? Or enter and exit, yeah. So if I'm entering the room, right, I'm bringing the energy in. If I'm exiting the room, what am I doing? Taking the energy out, right? So thermic, that's just thermal, that's just heat, right? So endothermic means bringing the heat in to the source, to the sample of matter, and exothermic means giving the heat off, right? Giving the heat off, okay? So that's how we go. When we go from a lower state or lower phase of matter to a higher phase, we're endothermic. You have to take in energy to get those molecules to move more, right? We go from a higher phase, energy phase, to a lower energy phase, we're going to release that energy, right? So that our molecules will settle down. All right. Phase changes involve a change in volume, but not mass, okay? Who remembers the conservation of mass? How does that go? Matter cannot be created or destroyed. It can only do what? Change form. That's right. And that is the premise for this, okay? Matter cannot be destroyed. Mass doesn't disappear, right? It just changes form. We might think that the puddle in the street disappeared, but what did it actually do? It evaporated, right? And it became a gas. It didn't disappear, okay? It just became something else. And adding and removing energy from matter results in a phase change. Endothermic, exothermic. That's how you get a phase change. Okay, it's not spontaneous. All right, last concept. Thermal expansion. Okay, just think about that word, thermal expansion. What do you think? Think about that term, thermal expansion. What do you think that means? What's thermal mean? Heat, okay. Thermal expansion, what do you think? If something gets hot, what happens? It expands, right? And that's exactly what happens, okay? So if you notice, when things get hot, they tend to take up more space, right? They expand. Well, this concept is used a lot in structural engineering, right? Because when the temperature gets really hot, the concrete and the asphalt in the roads expand, right? And when it gets really cold and it ices over, that same concrete asphalt mixture does what? Contracts, right? Now, have you heard on the news they talked about all the bridges that they're replacing in Alabama? We have a lot of really old bridges that need replacing, right? Because they were built before we understood this concept, right? So as this concrete or as these mixtures and the wood, some of them are that old that they're actually wood, expanded and contracted, it just continued to deteriorate the bridge, right? So it no longer could hold. Now we put these expansion joints in, and that actually allows, have you seen them in the roads and the highways and on the bridges? I want you to start looking for them. You'll see them. it allows for that expansion and that contraction so that the bridge can still hold, right? And it will not deteriorate. They put these little expansion joints in, okay? They also do it in construction, right? Have you heard the house creaking at night ever? Like there is some expansion and contraction depending on temperature change and whatnot. So we've got to build that in, but we didn't always know that. We didn't really always understand that concept, but now that we do, structural engineers use this concept to improve the integrity or the strength of our construction. Yeah? All right. Any questions? Okay, that's pretty much the overview of what we're going to be studying this week and next week, okay? So there's a lot of vocabulary in that, so make sure that you're going back through that and reviewing that vocabulary.
Wait, what's
That's a bridge, right? And you can put your